So again, we're on page 501 now looking at the ionic crystals, and we're going to figure out how many of each ion are in an ionic crystal. And then we're going to talk about covalent crystals versus molecular crystals. Both of those deal with molecules, but they are not the same crystal type. And then we're going to talk about metallic crystals, which was the last example we had with the gold metal. So there's the sodium chloride that we saw in the video, and as you can see, it's that large lattice structure repeating unit. So let's try this out. This example problem is on page 504, and they have provided the image here. That image is on page 503. And this is zinc sulfide. And so the question is, how many of each ion is contained within a unit cell of zinc chloride? So if you look on page 503 at the image for zinc chloride, then you can see here the chloride ions are these large yellows, and the zincs are the small silver ones here. So if we're looking at, in terms of the sulfides, the yellow ones, which one of these three is this? Simple cubic, face-centered, or body-centered in terms of the yellows? Face-centered, good. They're embedded in the face. So if it's face-centered, then how many ions are going to be there of the sulfur? So sulfur, face-centered cubic. So face-centered cubic, it's on the corners. So how many corners are there? 8. 8 corners to a cube. And each corner is what fractional amount inside of the atom? An eighth. So 8 times an eighth. And then you also have the faces. How many faces are there on a cube? 6, good. Each face atom is what fraction? Half, good. So how many, where did that, come on. How many sulfur atoms are in this? 4, good. So there are 4 of the sulfur ions. Now let's look at the zinc. This is sulfur 2 minus and zinc 2 plus, yeah. So now looking at the zinc, now we're looking at this silver one. It's a little bit trickier since it looks like it's on the inside. But still, if you're looking at the repeating unit, if you made one of these the corners, it's still going to end up being that face-centered in terms of the zinc. So zinc is also going to be, in this case, 4.
Wait, can you explain that one more time?
So, well, if you want to think of it as the larger cube, you can just look at the whole cube and count how many zincs are on the inside of one cube. So how many are there? 4. There's 1, 2, 3, 4. So there's 4 zinc ions on the inside. Rather than trying to picture, well, what would it be if zinc was on the corners instead of the sulfur like she did in the video? It's much easier when you have that, three-dimensional structure to look at bigger, but in this case, it's probably just easier to count them. And I would give you the image, of course. Yeah. 4 zincs and 4 sulfide ions. Any questions about the ionic crystals? So it's the same thing that we did last time, just you have to consider in terms of each ion what the cubic cell looks like. All right, so let's looking at those density versus the edge length thing again. Given that the edge length of a sodium chloride unit cell is 564 picometers, determine the density of sodium chloride in grams per centimeter. So that's 564. Let me start up a new slide here. Give us some space to calculate. So we're told that the density is 564 picometers. And that we are sodium chloride. last time when we were calculating the density, what was our equation that we made up for the density? Density is equal to what over what? Good, mass over volume. And last time we did that in terms of the unit cell, and we took the mass over volume and made it more specific to a cell. So what do we end up having on the top to calculate mass? That would be in the denominator. The Avogadro's number was in the denominator. Let's see. Yeah, molar mass times Z, where Z is the number of each atoms. Molar mass times Z, and on the bottom it was Avogadro's number times what? The side cubed, good. All right, so 564 picometers, that is our side. Of course, it's not going to be the unit that we want. Stop doing those horizontal lines. So we need molar mass and we need Z, and then of course Avogadro's number is a constant. So in this case, last time we had just the one, now we have two different things. So we need the molar masses of both the sodium ions and the chloride ions multiplied by how many of each one of those atoms are there. So in the case of sodium chloride, remember from the video, how many sodium ions were in each crystal? It was the first one she did in the video. Each sodium ion had how many? 4, good. So sodium, for sodium, Z is equal to 4. What is the molar mass of sodium equal to? Good, 22.99 grams per mole. Now chloride, how many chloride ions were there in that crystal? 4 also, good. And what's the molar mass of chloride? So each crystal is going to have, each cell is going to have both 4 sodium ions and 4 chloride ions, and we have to add them together to have both of them as the mass. So when we plug into here, M times Z, we're going to have it for both of these. The other thing we have to do is picometers. Is that the unit we want? No, when we're doing density, what are the units we want? Grams per, good, centimeters cubed. So we need to get those picometers to centimeters. A picometer is equal to what in terms of meters? What does pico mean? 10 to the what? Negative. It's smaller than a nanometer. A nanometer is 10 to the negative 9. 10 to the negative 12th. Yeah. So 1 picometer is 10 to the negative 12 meters. So we can take that to meters, 564 picometers. Let's do the railroad track method because we want to get all the way to centimeters. All right. So railroad track method, we want to get from picometers to centimeters. In my first part right here, what unit goes in the bottom? Picometers, good, so they cancel. What unit am I going to put on the top? Meters, because I don't know directly from picometers to centimeters. Then I'm just going to drop them down from my factor, 10 to the negative 12th. Goes up here, 1 on the bottom. Now picometers cancels. Next one, what unit is going to be in the bottom? Meters, what's going to be on top? Centimeters. What's the conversion factor between centimeters and meters? Are we certain? How many years in a century? 100. How many cents in a dollar? 100. What does cent mean? 100. So a centimeter, how many centimeters in a meter? 100. Okay, we feel good about that now? The metric will be the downfall of this country. At least it was the downfall for the Mars rover. All right, so 564 times 10 to the negative 12 times 100 is what? terms of centimeters. Negative 10th, close though. The conversion factors end up being 10 to the negative 10th collectively, but you still. Close. 8th. Okay, negative 8th. All right, 10 to the negative 8th. All right, any questions about that? Now everything's in the right units. Now all we have to do is plug that all into our formula there. Which I'm going to need another slide now. All right. Everybody have the numbers down? Ready? Okay. So again, our density is equal to the molar mass times Z over Avogadro's number times the side length cubed. In this case, we have for sodium ion molar mass times Z. So molar mass of sodium was the 22.99 times its Z was 4. What is up with those horizontal lines today? Go away. Plus, for the chloride ion, 35.45 times also 4. And the bottom Avogadro's number is what?
6.023.
And, oh, units. This is grams per mole. These are atoms. Grams per mole, atoms. And this is in atoms per mole. And then the last one, that edge length cubed. So our edge length is 5.64 times 10 to the negative 8th centimeters. Yeah. And then we need that cubed. Whew. Plug all that in the calculator and hopefully get something that looks like a density. These units, we're waiting. Atoms will cancel, moles will cancel. We'll be left on the top with grams, and on the bottom with centimeters raised to the third, so centimeters cubed. Which is good because that's our unit for density of a solid. As I always said last semester, it's very useful to know what kind of number you're looking for. You're looking for a really big number, a really small number, something in between. So what is the density of water? Ish. 1. So is salt more dense or less dense than water? More dense. So we're looking for some number bigger than 1. Now, is it hugely dense? No, so not hugely dense. So we're looking for a number bigger than 1, but we're not looking for like something that's like 100. Anybody get a number that sounds reasonable? Good. 2.16 grams per centimeters cubed. Anybody's calculator giving them something different? Good about that. So that's ionic crystals. So last time we did a metallic crystal because it was gold. Now we're doing an ionic crystal. So only difference is you have to add on the numerator, you have to add both ions together. Other than that, same thing. 2.16. Again, they do it stepwise instead of having a formula. Answer's the same, whichever method you prefer. If you prefer using the formula that we made, or if you prefer doing stepwise, whichever way, as long as you get to the right answer, it's fine with me. All right. Covalent crystals. So we've dealt with metals as crystals. We've dealt with ionic compounds as crystals, but you can also get crystals from things that are molecular, and there are two different kinds of crystals you can get there, covalent crystals versus molecular crystals. So covalent crystals, the atoms are held together by, as the name would imply, covalent bonds. Now what's stronger, a covalent bond or ionic bond? Ionic bond is held together by electrostatic attraction because one's positive, one's negative, like magnets. Covalent bonds are held together by what? What is inside of a covalent bond? Every time I draw a dash between two atoms, what's in that dash? Electrons. How many? Two. And what are those electrons doing there? They're being shared. Okay, so what makes a stronger bond? Sharing things or sealing things? Sharing. So what's stronger, covalent or ionic? Covalent. Good. So these are stronger bonds. So covalent crystals are stronger than ionic crystals. So the classic example is carbon. So what's the common name for crystallized carbon? Diamond, right? So what is harder and tougher and probably has a higher melting point if you thought about it? A diamond or a block of salt? What is stronger? Diamond. Diamond is stronger. Okay, so think about it this way. Covalent crystals are held together by covalent bonds, which are stronger than ionic bonds. Therefore, they are stronger crystals. And of course, carbon comes in more than one form naturally occurring. We have carbon, and then we have carbon as a diamond, and then we have carbon as graphite. Both of these are all held together by covalent bonds. Now the difference is the crystalline structure that makes the difference between a diamond, which is, at least in our society, very expensive, considered rare, versus graphite, which is pretty commonplace and relatively inexpensive. And that's whether or not you end up with this three-dimensional shape or this two-dimensional kind of layering of plates on top of each other. And that's why graphite is so soft, and why if you take a pencil and run it across paper, it's going to slough off some of these layers and leave it behind on the paper. And that's how pencil lead works. So these are very strong bonds. Now, another example of this is silicon dioxide. So silicon dioxide is, what do we use silicon dioxide for? Where do you find it? Glass. Good. Glass is made from silicon dioxide. Sand is made from silicon dioxide. Sand is very, very small pieces of quartz crystal. So silicon dioxide is quartz crystal, and glass is what happens after you've done what with that quartz? What do you do with sand to make glass? Melt it. And when you melt it, it rearranges these bonds. So I had a second video. Don't worry, it's a shorter video. I was going to show you. Keep that to look at silicon dioxide. All right. So the silicon dioxide crystal structure is like the diamond, except similar to an ionic compound. You've got two different elements going on here: the silicons and the oxygens. So the silicons are the ones shown in blue here. The oxygens are the ones shown in red. So there's twice as many reds as each blue here. So you end up with this large three-dimensional structure. However, when you melt this down, it breaks all those apart, and they end up reforming in an amorphous network. And we're going to see amorphous solids in the next section, but I just want to show you the pretty animation of the silicon dioxide crystals. So that's a quartz crystal there. Molecular crystals, on the other hand, are not held together by covalent bonds, although they do contain molecules that have covalent bonds within their structure. Classic example of this is ice. Ice is a crystal. It's made out of water, H2O, which is molecular. However, what is going to be stronger, ice or a diamond? Diamond's much stronger, so what's the difference if they're both molecular? What's different is what makes the structure of the three-dimensional crystal. In the case of the diamond or the quartz, it was covalent bonds. In the case of ice, what did we learn last time holds together H2O molecules? Hydrogen bonds, good. So these little dotted lines right here, those are hydrogen bonds, not covalent bonds. Hydrogen bonds are intermolecular forces. They are the strongest of the intermolecular force compared to dipole-dipole and dispersion. But still, compared to ionic bonds or covalent bonds, they are weaker than ionic bonds or covalent bonds. So that is why ice has a relatively low melting point. These things can break apart, and of course, it's brittle compared to such a diamond. Back up there. So be able to distinguish between a molecular crystal versus a covalent crystal. Yes?
Less strong than covalent or ionic?
It's the weakest compared to the three. Yeah. Covalent is stronger than ionic, which is stronger than molecular. Yeah. Because compared to ionic bonding, hydrogen bonding is still weaker. Now you can have molecular crystals that don't contain hydrogen bonding as long as it has some sort of van der Waals force. Again, the van der Waals forces are dispersion or London dispersion, dipole-dipole, and then the hydrogen bonding. So one of those things holding them together. So that's a molecular crystal. Metallic crystals. Now we had an example of this in the last time when we did the density of gold, but we didn't really talk about what the difference is. Metallic crystals are these large three-dimensional networks of metal atoms, but they're not bonded covalently and they're not bonded ionically, so what is holding them together? They're generally held together by the attractive forces between the electrons around the atoms and the protons inside of the nucleus there. So they generally end up being body-centered cubic, face-centered, or the one that we didn't really talk about in detail, the hexagonal close-packed structure. We're going to focus mostly on those two, the body-centered cubic or the face-centered cubic, those two kinds. Now in this case, the electrons aren't exactly shared the same way they would be shared in a covalent crystal or covalent bond, but they're also not really transferred like in a ionic. Instead, what happens to them is something called delocalizing. See, delocalizing means that all of the electrons are just going to kind of cover the entire structure, just kind of, but not really belong to any one specific atom, but also not being shared between two specific atoms like a covalent structure. Instead, they're just going to kind of be delocalized all over the whole structure, and all of those electrons that are delocalized can be moved around a lot. And that is why metals make such good conductors of electricity, because those delocalized electrons are running around free on the outside, so electricity can run through them very easily. So this table just summarizes those four crystals we talked about, what the cohesive force, or in other words, what holds together the crystal, the general properties, and some examples. So that table is on page 507. Let's try one more example. This one should be even easier than the last one. So this example is on that same page. Now we're going to find the density of iridium, so a metal crystal. So same as the last problem, except now we just have one thing to worry about instead of two. So instead of sodium and chloride, we just have iridium. So the metal iridium crystallizes with a face-centered cubic unit cell. Given that the length of the edge of the unit cell is 383 picometers, determine the density in grams per cubic centimeter. So I want you guys to try this one because it's easier than the last one. You've only got one element to worry about. By the way, iridium is number 77 up there if you're trying to find it up there. So go ahead and try that on your own. Anybody stuck, or how are we doing? Feel good? Have an answer? What I got? Good, 22.7 grams per centimeter cubed. Anybody not get that answer? Something different. All right, ready to be done with crystals for a while? So amorphous solids, talk about that silicon dioxide very briefly. Silicon dioxide, again, that quartz structure, but what happens if you melt it down and then cool it to make glass? So here's our silicon dioxide looking at it two-dimensionally instead of three-dimensionally like we had in that video. Now, this is the quartz, but if I melt it, I break a lot of those covalent bonds to make the liquid, the molten silicon dioxide. When I cool it again to make glass, it's going to reform those bonds. Now, did it reform it in an organized structure like before? No. So between quartz versus glass, which one is stronger? Quartz. A quartz crystal is going to be stronger than the glass because this amorphous structure is going to be weaker and be more brittle, which is why glass breaks easier. So I'm not going to ask you anything too detailed about amorphous solids, and that is all of section 11.5 right there. So moving on to section 11.6, so I only got 2 more sections left. Now we're going to talk about the transitions between the states of matter. So we've talked about gases in chapter 10, and in this chapter we have talked about liquids and solids, and now we're going to talk about transitioning between those 3 phases and what happens at each of those transitions. So phase change we've been talking about since chapter 1. It's a physical change between one state of matter to another. And it's something like going from a condensed phase, like a solid or a liquid, to a non-condensed phase, the gas phase. Again, we're just going to focus on the 3 big ones, solid, liquid, and gas. We're not going to worry about the specialties like plasma. They're usually accompanied by an energy change, either adding energy or releasing energy. So we gave the example before of the heat being required versus lost. Again, requiring heat is endothermic, losing energy is exothermic. And now we're going to actually be able to calculate what that energy is. So the energy associated with that is the molar heat of either vaporization, if you're evaporating or boiling, or fusion, if you are freezing or melting. And then we also have sublimation from a solid directly to a gas. We have condensation, which is the opposite of evaporation. Fusion, by the way, usually means freezing. Fusion, fusing together. So evaporation and condensation are the exact same thing, just the opposite. So in chapter 5, when we were first learning about endothermic versus exothermic and the enthalpies associated with it, what happened to your delta H, your enthalpy value, when you reversed your equation? What happened? Flipped what? The sign. Good. You just flipped the sign. So it's important to note when you're looking at these phase changes, any phase changes that are the opposite of each other, the number is going to be the same, just switched in sign. So that's why melting and fusion here, you're going to have the same, or melting versus freezing, you're going to have the same delta H, just switched in sign. It's not a table, it's just an example on page 509. Yeah, it's just in the middle of 509. Yeah. Table 11.6 is the actual values for these. All right. So when you are going through here, melting or fusion from liquid to solid, you're increasing your temperature, keep on increasing the temperature, you're going to vaporize, or you can completely bypass the liquid phase, go from solid to gas for sublimation. And then here's the opposites. Deposition is from gas directly to a solid. Condensation, of course, from the gas to the liquid, such as at the outside of a cold glass. And then freezing. So, melting points versus boiling points. So boiling points we normally think about as water boiling at 100 degrees Celsius. Of course, that's the normal boiling point. What factor can change the boiling point of water? Pressure. Good. Change pressure, you change the boiling point. So when we talk about boiling point, we're going to be referring to the normal boiling point. For the purposes of this chapter, we're going to assume we're at 1 atmosphere unless otherwise stated, so that we can just use the normal boiling points and melting points. The molar heat of vaporization, delta H vaporization, is the amount of heat it takes to take 1 mole of a liquid and put it into the gas phase. This takes a lot of energy, a lot more than was associated with just a temperature change back in chapter 5. It's going to take a whole lot more. So delta H's of vaporization are generally bigger than the delta H's we were dealing with in chapter 5 that were just a temperature change. By the way, because we're going to need it, quick recap of chapter 5. Q is heat. What was our formula for the heat associated with a temperature change, or a delta T? What was that equation again? Because we're going to need it. Q is equal to what? Good. SM delta T. Remember we said Q is equal to SMAT. However it takes to remember it. Q is equal to SM delta T, where S is the specific heat of the substance, which for water was 4.184 in the liquid phase. M is the mass of the substance in grams, and then delta T is whatever the change in temperature was. So that is to calculate the heat or enthalpy of a temperature change. We're going to have bigger enthalpy values for the molar heats of vaporization, but if you were changing phases, generally you're going to do both changing a temperature and changing a phase, so you do have to keep track of both of them here. So the boiling points and delta heats of vaporization of common substances. There's water on the bottom. Of course, it's 100 degrees Celsius is the normal boiling point. Its molar heat of vaporization is 40.79 kilojoules per mole. That's a huge number because that's in kilojoules. That's 40,790 joules. That's a big number. And that's just for 1 mole of water. By the way, 1 mole of water weighs how many grams? That's the density, but how many grams does 1 mole weigh of water? What do we call that? The mass of 1 mole. It's what mass? Molar mass. What's the molar mass of water? Good, 18.02. So when we're dealing with this, that's how much it takes for 18.02 grams, which is 18 milliliters. That's not a very big volume, to vaporize. So remember, water is about 1 gram per milliliter, so 18 grams is about 18 milliliters. That is not a very big volume. A tablespoon is 15 milliliters, so that's just bigger, slightly bigger than a tablespoon. That's how much heat it takes to vaporize just a small amount of water, just to put this in perspective. We're going to be mostly dealing with water, unless otherwise I will give you the values so you don't feel like you have to memorize this table. All right. When you are trying to go into the gas phase or into there's at some point you hit a temperature where you cannot stay in a condensed phase. You can't stay in the liquid phase, and that's the critical temperature. The temperature at which it is so hot you cannot get your liquid, say water, back into the liquid phase. It's got to be in the gas phase. It's just too hot regardless of whatever pressure it is. Likewise, you have a critical pressure, which is the minimum amount of pressure you must to get that, if it's right at that critical temperature, back into the liquid phase. So if you end up getting a fluid that is exceeding its temperature critical and its pressure critical, this is technically called a supercritical fluid, which some people consider its own state of matter. We're not going to really deal with supercritical fluids. That's just a definition, just to be aware of. And these definitions are also on page 510, so don't feel like you have to copy them down right now. I'm trying to get into, and these are just examples of critical temperatures and critical pressures of different substances. So we've talked about the phase change vaporization. Now let's talk about melting or fusion. So melting point and freezing point are actually the same temperature because that's the point at which you end up right at the equilibrium. So right at the freezing point or melting point, which for water is what in Celsius? 0. You have an equilibrium between the phases. So water can be both liquid or solid right at 0 degrees Celsius. You end up with this equilibrium right there. So both liquid phases and solid phases coexist there. So for water, it's again 0. And then just like for vaporization, we're going to have a molar heat of that phase change. In this case, is molar heat of fusion or melting. So 6.01 kilojoules per mole. So it takes less energy, in other words, to melt something than it takes to boil it. Makes sense. It's easier to melt ice than boil it. So again, for vaporization, this was 40 compared to just 6. Supercooling is where you can get a liquid to be cooled down below its freezing point without it going into the solid phase. Again, this is done by changing the pressure. All right, here's what we're getting to. So this image is on the bottom page 511. This is called a heating curve. A heating curve. It compares as time goes on what is happening as you heat a substance. So in this case, this curve starts down here at time 0 as a solid at some temperature lower than the freezing point. And you start increasing the temperature. So as time goes on, you're increasing the temperature until right here you get to the melting point. At the melting point, then, you're going to plateau for a while. The reason it plateaus is because you cannot increase the temperature of that solid until it has all melted. So as time's going on, what's going on right here is it's melting. And while it's melting, it's absorbing a lot of heat, but it's not changing its temperature. It can't change its temperature until it is all in the liquid phase. Once it's all in the liquid phase, then we can start increasing our temperature again. So temperature goes up, 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 until we hit, here's the boiling point. So at the boiling point, same thing, we're going to plateau. And at this point, while we're plateauing, we're feeding more and more energy into it, and all that liquid is going into the gas phase. We can't increase the temperature of it until we get it all into the gas phase. So unless you pressurize it, water cannot boil at a temperature higher than 100 degrees Celsius at atmospheric pressure when you're dealing with pure water. Then once it's all in the gas phase, that vapor can then get hotter. So unless you're pressurizing it, steam can be hotter than liquid water. But you cannot have water hotter than 100 degrees Celsius unless you change another factor such as the pressure, or as we're going to deal with in the next chapter, if you add something like salt to the water. So this is a heating curve. Now, at any point in this heating curve, we can calculate the energy that's happening. Everywhere where you have a positive slope here, you are increasing the temperature, so the temperature's changing. How do we calculate the heat associated with the temperature change? Good, SM delta T. So everywhere you are changing the temperature, you can calculate the heat associated with that portion of your graph using Q is equal to SMAT. Any phase change, though, you're going to need that molar heat of fusion or molar heat of vaporization. So here at the melting point, you're going to need your delta H of fusion. Now that's per mole, so I'm going to put times N, so times however many moles you have. And then up here it's going to be the same thing, but for vaporization. Delta H vaporization times and however many moles you have. Sublimation, we didn't really talk about that in detail. That's the example of dry ice. You have a solid that goes directly into the gas phase, and then its opposite deposition from a gas directly into the solid phase. So here in this globe right here, we have iodine. That iodine in gas phase is kind of a purplish color, so that's what the purplish color is coming from. It's the gas phase iodine. But on the edges of the glass here, instead of condensation where it goes to a liquid, this is actually solid iodine. So this is inside this globe. It's at the correct pressure and temperature to be at equilibrium between the gas phase and the solid phase. Because deposition or sublimation bypasses melting, it's technically the sum of melting and vaporization according to Hess's law. So Hess's law back in chapter 5, I know you guys loved that. Don't worry, we're not going to do that again. Just going off of what the law states is that if you can take a thermodynamic equation, break it up into smaller reactions, the enthalpy of the overall reaction is the sum of the individual enthalpies. So sublimation could be written as the sum of fusion or melting and vaporization. So you just add their delta H's together. So you won't see a table of delta H's of fusion or of sublimation because you can just add your fusion and your vaporization to get those. All right, let's try an example here. So we're on page 513. Calculate the amount of heat deposited on the skin of a person burned by 1 gram of steam at 100 degrees Celsius. What's worse, being burned by boiling water or being burned by steam? Anybody know? Which one's a worse burn? Steam. Even if they're both at 100 degrees Celsius, boiling water and steam, in this case the steam is only 100 degrees Celsius, it's actually going to transfer significantly more heat to the skin than boiling water would. Because boiling water transfers just the temperature to your skin. Steam, when it hits your hand, it's going to condense from gas to a liquid. Condensation, is that endothermic or exothermic? Does it absorb heat or release heat? It releases heat. Where is it going to release that heat into? You. So it's not just the temperature, it's also the phase change is going to release heat. That's why steam burns are so much worse than just boiling water burns. So we're going to see exactly how bad this is. So the amount of heat that is released is going to be the phase change here. So we need first to take those grams and convert them to moles. And I feel like we need more information there. What's the temperature of the person's skin? Where did they get a temperature change from? 37, where does it say that? Way down. Yeah, I feel like that should have been like right in there in the problem. Oh, yeah, it says in the problem, it didn't put it on the slides. That was nice. So assume that the person has a temperature of 37 degrees Celsius. Yeah, not quite sure why I skipped over that. Okay, so we've got two things going on here. Both the water is going to have to come down to the temperature of the person, and it's got to condense. So there's two different phases. Looking back at our diagram here, we're going to have this phase change where we're going to go from a vapor to a liquid, and then we're going to have this temperature change where we're going to go down, in this case, only down to 37 degrees. So we're going to have this, and then we're going to have this. The total amount of heat deposited on that person's skin then is going to be the sum of both the phase change and the temperature change there. So let's do the phase change first. So the phase change, that's delta H of vaporization times N. N is the number of moles. So how do we find moles? Good, divide by molar mass. So I've got how many grams of water? 1 gram of water. Divided by 18.02 grams per mole gives us how many moles of water? Yeah, 0.055 repeated, so we'll just round that. 0.0556 moles. So for the first amount of heat, what is delta H vaporization for water? What was that number again? Good. 40.79 right there from that table. 40.79. And that's in kilojoules per mole. And now we're going to multiply it by moles, 0.055 repeated. We'll just round to 6 here. And that'll just leave us with kilojoules. Now, am I vaporizing here or am I condensing? You're condensing. So if this is the molar heat of vaporization, what do I need to change about that number to make it condensing? Make it negative. Good. So we're going to put a negative out front here. So negative, I'm getting 2.266. 266. And moles canceled, so we're just left with kilojoules. Now let's do the second one, which is the temperature change. That was the SM delta T. What is S, the specific heat of water? Well, now we probably haven't seen that one since chapter 5, but it's 4.184. And that's in units of joules per gram degrees Celsius. M is just the mass, so we don't have to convert that to moles. We can leave it in grams. That way the units will cancel. And then delta T, if we're going from 100 degrees Celsius down to the body temperature, which is 37, what change in temperature is that? Positive or negative? Negative, good, because we're dropping in temperature, so negative 63 degrees Celsius. Change color here, units. Grams will cancel with grams, degrees Celsius with degrees Celsius. So what unit do we get from the second equation here? Joules, good. Negative something. I'm getting negative 263.6. And we're left in joules. So the total amount of heat deposited on that person's skin is going to be the sum of these two. What do we need to do, though, before we add them together? Good. We need to put 263 in kilojoules because you can't add things that are in different units. So what would this be in kilojoules? Divide by 1,000, remove the decimal, how many places? 3. So negative 2636 kilojoules. Now we can add them together. So Q total. Getting negative 2.53-ish. Kilojoules. So that's the amount of heat that was deposited. Well, the amount, we would just leave off the negative, but. Now, if this had been boiling water that touched their skin, it would have only been the change in temperature. So it was tenfold worse when it was steam versus if it had just been boiling water. Or not tenfold.
So if it was just
Yeah.
boiling water, you would use just the SMAT or?
Just the SMAT because there was no phase change if it was boiling water. So that's why steam burns are so much worse than just a boiling water burn. Now, I could have given you a problem that had more steps. This one just had two, one phase change and one temperature change. I could have given you this problem. Everybody got this down before I move away from it? I could have given you this problem that had more of the steps from our heating curve here. I could have asked you how much heat is required to go from, say, this temperature is a solid to this temperature is a gas, in which case you would need to add the Q from that part to the Q from that part to the Q from that part, plus the Q of both of these phase changes. So if I gave you a more complicated one, it just keeps on adding them up. Just add up each steps. And I recommend going ahead and drawing a heating curve so you can keep track of how many steps you need to add together. So starting at whatever temperature and phase, increase it till you reach whatever the temperature is that phase change occurs, plateau, and then just keep on going.
What page is that on?
The heating curve, this one was on page 511. All right. If we have time, I'll do an example of that. We'll do phase diagrams real quick. If we have time, we'll go back. Otherwise, we'll do an example of that next time. All right, last section, phase diagrams. Don't worry, there's no calculations to do with this. So phase diagrams show you pressure versus temperature, what phase to expect your substance to be in. So every substance will have its own unique phase diagram. So here's the phase diagram of, which one is this? Did it not say? This is carbon dioxide. So here we have at 1 atmosphere of pressure versus negative 72 degrees Celsius is where you transition from being a solid to a gas. So at 1 atmosphere of pressure, if you can cool it down enough, you can get carbon dioxide to be a solid. Of course, we're familiar with that. What do we call solid carbon dioxide? Dry ice, right? So this is dry ice. But once you let that be at a temperature higher than negative 78 degrees, what's that dry ice going to start doing? So say you're over here like at room temperature. You take that solid, put it in room temperature, it's going to turn into what phase? What phase is this? Vapor. It's going to go into the gas phase. Did at any point in time it go into a liquid phase from solid to the vapor? No, so what do you call that phase change? Sublimation, good. So this is showing you the pressure versus temperature where you're going to have different phase changes here. So along this line here between the solid and liquid, this is all your melting points. So as it changes with pressure, from the liquid to the vapor along this line, these are all your boiling points here. And then of course down here your sublimation points. Right here in the center where all three meet is called the triple point. So every substance has a triple point, which is the point at which all three phases can exist in equilibrium. And that's a very specific temperature and pressure for every substance. Now for most substances, as you increase the pressure, what is happening to your melting point as you're increasing the pressure? Is it going up or down? most substances, you increase the pressure, is it going to have a higher melting point or a lower melting point? Going up, does this number get higher or lower? Higher, right? This is a positive slope. That means it's increasing. So it's getting higher. For most substances, this is true. You're going to, as you increase the pressure, it's going to melt or go into the liquid phase at a higher temperature. In other words, it wants to stay solid as you're compacting it. As you're squeezing it with higher pressure, it's going to want to stay a solid. Most substances do this. There's one very notable exception to that. This is water. Notice we go from the slope being positive here to, in water, the slope did what? It's negative, which means that water, as you increase the pressure on solid ice, what's going to happen? Is it going to want to become a liquid or stay solid? It's going to go into the liquid phase. Most substances want to stay solid as you compress them, because most substances, the solid phase is more dense, so squeezing it, pushing the molecules closer together, is going to favor being a solid. What's special about water, the density of its solid versus liquid? It's less dense, and that's because of those hydrogen bonds forcing it to spread out in that crystalline structure. Ice, solid water, is less dense than liquid water. That's why ice cubes float. And this creates this unique phase diagram here where you end up favoring the liquid at high pressure instead of favoring the solid at high pressure. And then here, again, we have our triple point here. For water, you have to be, look at this, very extremely low pressure in order to get it to sublimate. You can't sublimate at any pressure less than 0.006 atmospheres. Again, 1 atmosphere is normal pressure. So you have to lower the pressure really, really low to get ice to go directly into the gas phase from the solid phase.
Can you say one more time what page this is on?
This image is on page 515. Yeah. All right, so using a phase diagram, now I would show you the image of the phase diagram, determine the normal boiling point and the normal melting point. By normal, I mean what? 1 atmosphere. Good, so pressure is 1 atmosphere. And then determine what physical state it would be at 2 atmospheres and 110 degrees Celsius, and then the triple point of the substance. So let's first determine the boiling point and melting point of the substance. All right, so here's our phase diagram. So to determine the normal melting point and normal boiling point, that's where the phases change at 1 atmosphere. So I'm going to just draw a horizontal line where we have 1 atmosphere pressure across. Of course, there's going to have to be an estimation here. So this phase is what? Melting or boiling right here, where that red line. Melting, good. So the normal melting point of this substance is about what? Ish. 130, 140, something like that. What's their estimation of it? 140. Yeah, they say about 140. Whereas the boiling point here would be right here, so just higher than 200 would be the normal boiling point here. They estimated 205. So any questions on how to estimate the normal melting and boiling points from a phase diagram? On that one? Now let's determine what state of matter we would be at 2 atmospheres and 110 degrees Celsius. So we're going to draw a horizontal and vertical line here. 2 atmospheres, we'll draw a horizontal line. And then a temperature of 110 degrees Celsius, so we'll draw a vertical line at 110 degrees. So right there is where those two meet. What phase is that? Solid, good. So the answer would be, it would be a solid at that temperature and that pressure. So if they give you a temperature and pressure and ask you what phase, just draw where draw the 2 lines where they intersect is your phase. And then the last one was, what is the triple point? So the triple point is right here. So that's like 0.7 something, about 0.8 atmospheres. Yeah, about 0.8. And they said 115 degrees Celsius. So from a phase diagram, be able to identify those three things.